excellent point. And I'm going to get to that in detail. So it's one of the real analyses, because that's actually a conventional kind of assumption. And it's been passed along for so long that even Richard and others were kind of surprised. So the quick and dirty answer is, if you have a single file system, so if you create a ZFS pool, by default you have a single file system. And if you actually do, and we'll show, actually I run roll traffic and measure, is that it is predominantly sequential. It's not 100% sequential. But for most users, that's the exception, not the rule. Most users have more than one file system. And because, again, every file system has its own so-called ZIL, and they all have to share the same ZIL accelerator, just imagine all that traffic from these independent file systems, which there's no synchronization among those. So when you aggregate that resultant traffic, basically what I'll show shortly is that it trends to random. So, and I can give more details once we get to that slide. But that's a good point. And that would be critical. So if it stays sequential, and then actually any SSD would have less impact. But it's even more. Yeah, true. I mean, there's still some latency issues, some benefits, but it's definitely mitigated. But the moment you have a random quality, and then that's where you have these orders of magnitude differential and performance impact. So excellent. I don't want to talk too much because it'll kind of kill what we'll talk about. Again, this warning. And it's not just, do they actually handle the synchronized cache or flush cache commands, because they have to implement that well. But then the corollary, and it's just as important, is so if you send that cache flush command, but the device doesn't power protect its volatile caches, then it's going to get that command. Let's say the host power loses. It can't actually finish it if it can't power protect its volatile caches. So it's really dual. You have to, a proper device has to offer both. It has to actually consistently and without fail implement synchronous cache and be able to power protect all its components, or data loss. And there's too many devices, and we'll show a few examples, not beating up anyone. But every SSD sold by Intel does not power protect their volatile caches. Now, what they actually, and it was interesting to hear in the panel, he said that we don't actually use that for a so-called normal cache, but on ZFS Discuss, there's many examples of basically they use it for something, and they won't actually say exactly what they use it for, but the end result is that transactions are lost if you yank the power. So what you're looking for a ZIL device, without a doubt, is you have to power protect volatile caches, or you can't satisfy cache flushes. If you can't satisfy cache flushes, you can't satisfy synchronous writes. If you can't satisfy synchronous writes, that's the whole premise of the ZIL Accelerator and ZFS itself. So it's kind of a, it all builds on top. Here are two devices, and they're both based on the most recent SandForce 1500 controllers that have onboard supercaps. So they deserve to be commended for actually taking that next step and protecting users' data. And I think they're great examples because the 2EX, which is a very, very new product, is based on SLC, and then the Pro, which has been out slightly longer, is based on MLC. So I want to give them kudos for power protecting caches. Again, this is really technical here, but the log bias. So we talked about every ZIL shares the same ZIL accelerator, so that's really a critical resource. So basically what this is kind of a complicated, but I just simplify it for you. This enables you to dictate which ZIL actually uses the ZIL accelerator and which doesn't. And if anyone has more questions, we can talk offline because it's pretty technical. But in essence, it enables you to determine which file systems would actually utilize your very critical and expensive ZIL accelerator. And in summary, basically if you set log bias to throughput, you're basically taking heat or I/O pressure off of the ZIL accelerator for that file system. So, and there's many cases where you have a file system, some databases could be using a single file system, be extremely synchronous write bound, others not so much. And this gives you the ability to kind of a granular control to dictate what gets sent to the ZIL and which would actually get accelerated. Again, this is no one else talks about this, so I think this is kind of interesting. Why does the attachment interface matter? And this is kind of hard to explain because, again, there's not real terminology for this. But basically what we're talking about, and a lot of people don't realize this either, is a standard SSD, there's actually two controllers. So the data path from the SSD over the cable to the HBA controller to PCI, and then the benefits of basically a PCI product, similar to ours, which is the example I show here, full disclosure, is the idea of a single unified controller. And what doesn't get really talked about, and I kind of like this, it's BER, bit error rate. Every bus has a BER. It's impossible not. So not given enough credit is the benefit when one can remove an entire bus from a data path. There's actually really amazing ramification benefits, not just ramifications, but benefits. So as you can see, the red is collapsed. So you can basically take two controllers and remove a cable and collapse it to one. And it's kind of unique to this new style PCI Express device. I'll break these down, these benefits, in 2 slides. So performance, you go from 2 hops to 1. I mean, fundamentally, since you don't really want to hang your SSDs off the same controller you have your hard drives on, because again, you have these contentious paths, you really would love to dedicate a controller to your SSDs for maximum performance, especially for the L2 ARC and the ZIL. So in that case, actually, let's just say worst case you had 1 SSD and 1 controller. You're cutting everything in half, not just the path for performance, but the scalability of the ops. So what we're finding today, and controllers are definitely getting better, but you have these amazing IOPS capable SSDs, and you're hanging them off controllers that were designed for hard drives. And the question is, how many can you attach today and then even tomorrow before basically the true bottleneck is the HVA controller. So if you hang 100 Intel SSD drives, you're only getting a benefit for first 4 or 5, depending on the controller, maybe slightly more. But anything past that, your IOPS are basically stuck behind this controller that just wasn't designed to be IOPS intensive. And by removing that controller, like we do in our product, you'll see measurable performance, interesting results. Second is reliability. I mean, for enterprise customers, this is critical, and you just can't argue that fits, failures, and time. If you can remove, if you have 2 controllers, you can remove the 1, you've doubled your reliability. No bust, no burr. This leads back to your question, and this is actually critical when you actually compare the 2, flash and DRAM, because they fundamentally differ once you really hit true random. So what is the access pattern for the ZIL? And so what I did was, if you guys are DTrace familiar, I basically started with 2 DTrace toolkits, and then had to make some modifications to get this data. But IO pattern is actually a pretty cool DTrace script, and basically what I'm showing here is a single IO zone workload targeted at a single file system. And as we said, every file system has a ZIL. And as you were saying, as you can see, it is predominantly sequential. But also to point out, it doesn't take even those 1% and 2% on a sequentially, basically optimized device that really throws them for a loop. But what we can conclude, and this is conventional wisdom, is that the ZIL access pattern is predominantly sequential. Now, what we're going to find is that it turns out to be only for a very unique case, and that's if you have a single file system. But let's break this down. So this gives you one kind of view of the data, and I thought this was important enough to give kind of a second metric. So there's another DTrace script called seek size, which actually made some modifications to. It's really cool, and I actually had to split the data up into 2 slides. But if you're familiar with DTrace, you'll recognize this output. But not only does it tell you what % are random or sequential, but it gives you to what degree. So that baseline, that's showing you that most of the workload, the I/O is sequential, meaning the I/O hits exactly after the last one. But then you can actually see exactly once they do go random, to what degree off the last one. So it's an interesting data point. Again, almost all sequential. Here's the flip side. This just shows you plus and minus from the last. Gives you more insight into the level of sequentialness for this. But here's the real doozy, and this is what prior is definitely has opened some eyes, is once you go past that default single file system, even at a minimum of 5, you can see the workload pattern drastically changes. We're no longer sequential, and the randomness definitely varies. It's going to vary over workload. But what's pretty conclusive is, and here's these seek sizes. So this gives you a detail of exactly how random it is. Well, not random, but the distribution of so-called random, I guess. So we're showing basically the summation. This is a key point. It is predominantly sequential for a single file system. The moment one has multiples or even 5, you almost approach 50% random. So we have customers with thousands of file systems. So you can imagine the more file systems you have, you really have to start thinking about your workload as not being sequential, but being random. And that's a different thought process, and it directly affects kind of the conclusion to this presentation. So, Kurt? Sure. Okay. You say address ranges. Fine. Okay. Okay. You can. So basically, I think what you're asking is, can you associate a ZIL accelerator to a file system? And if you could, then you could basically dedicate a range on a per file system basis. And it's not possible within ZFS. So, and there's good reasons it's more technical. I mean, I've actually looked through Neil Pren, which is the gentleman's son that actually wrote the ZIL code. It's quite illustrative. So I think it's an interesting point, but he had good reasons for designing it the way he did, which definitely get far more technical than I want to go into here. But it's a good point, and I think the overall is that you can't associate a file system to a ZIL, and therefore you can't control the moment more than one talks to it. You can't control that aggregate random behavior. And this was not something that's going to change over time. This is fundamental, so it's kind of we're stuck with what we have. As I said earlier, this is probably the most controversial aspect. Let's dive in and please give feedback as we go. This is just a fun slide. At least I always thought it was fun. So we're talking about Flash and how Flash reacts to different I/O behavior. And I always thought it was interesting to kind of start with, you know, what really is the underlying aspect of Flash? Because it kind of fundamentally gets to the heart of this idea of degradation, which is the whole point of this question, is Flash degrades over time. And it'd be real interesting. I always thought it was interesting, why would it degrade? And it kind of comes down to just the basic physics. And so you have a table, you bounce the ball. Anyone tell me what quantum tunneling tells us? At one bounce, what could possibly happen? It bounces, it bounces, it bounces on the table. Quantum tunneling basically, and again, I'm sorry. Yeah, that's exactly what it will. Yeah. So quantum tunneling basically states, and this is nothing that, you know, this is all not opinion, this is commonly agreed, but it's kind of reality distorting, is that you bounce the ball enough times, and one of the times the ball will not, you know, crush or break the table, it just magically appears on the other side. And it's based on this idea of quantum tunneling. Now, for as strange as that sounds, is that you can bounce a ball, and if you bounce it long enough, now again, this would be nothing you could ever physically do because the numbers are just massive, but it will get on the other side of the table if you bounce it enough times. Now, for as crazy as that sounds, that is the basis of Flash. So if you notice, and I picked two pictures, those are electrons. Those are literally the equivalent of what that ball is. And the fundamental nature of Flash, so the ball on the table, and it's really moving electrons over a barrier. And these two absolutely brilliant gentlemen, Fowler and Nordam, they basically came up with math that lets electron tunneling, things just appearing at different places. They came up with the math, and then semiconductor technology allows us to basically create a barrier where we can control this and not have it happen every one in some huge number, but have it predictably happen. And that's how Flash works. So it's based on what is seemingly illogical nature, but the fact that it happens every time is just the bafflement of semiconductor technology today. So I guess I got more into that than other people did, but anyways. So how does a flash write differ from a DRAM write, physics aside? And this could be easily a presentation in itself, more than a presentation. So what I try to do is just summarize. I think what's most interesting, a lot of people don't realize, is with Flash, you can never write. It always requires a two-step process. You first have to erase, which is changing every bit to a 1, and then you have to program a 0. So unlike a hard disk or unlike DRAM, you can't selectively choose whether you want to write a 1 or 0. And that has massive ramifications and also plays in this whole basically factor of what we're talking about is why does it degrade? So every write will require two separate flash operations. The key to flash SSD performance is hiding or overlapping the erase. And there's lots of tricks and ways that they do that.